Hi there, this is Heath. We're looking at the day 20 notes on matchings. Let's go ahead and get started. When we talk about matching in a graph, we're looking at a set of edges in which no two edges share a vertex in common. So we can have an edge between a pair of vertices, an edge that matches another pair of vertices, but we can't have this sort of thing where this vertex shares two different edges. That's what's not allowed. So in this graph, all of these are matchings. The first matching, AB matches together, CD matches together, EF matches together. That's an example of a matching. M2 is also a matching if instead of matching these three edges, we match these three, BC and then DE and then FA. That's also a matching. This is also a matching, BC and EF. There are some vertices that are left over. That's okay. And then the last example, it's not a very good matching, but it's still a matching. No edge, no vertex has two edges. We have a lot of unused vertices. But it still meets the definition of a matching. A matching just has to match some of the vertices, maybe not all of them, but doesn't match any vertex more than once. And so all of these are valid matchings, including M4. Okay? These are not matchings. AB, BC, DE, and EF, these aren't matchings because vertex B and vertex E are repeated, and that's not allowed. This is also not a matching, AD, BE, and CF, because these aren't edges. I can't match a vertex to a vertex that doesn't have an edge between it. These are not edges. And so neither of these are valid matchings. I hope that clears up what the definition says. A couple of definitions. These two are similar, so I want to clarify the difference between these two. A matching is maximal if we cannot add any new edges and still have a matching. And a matching is maximum if it is impossible to find a matching in the graph that has more edges. These don't mean the same thing. And we go back to the previous slide and show you what I mean. If we look at this matching right here, M3, that's BC and EF. That's a matching because no vertex is used more than once, but I cannot add to this existing matching. I can't match D to anything. I can't match A to anything. So I can't add to what's already here. So it's maximal with an L. But it's not maximum because we only match two edges here, and it's possible to match three. It's not a maximum matching, but it is a maximal matching. Maximal, you are constrained to working with the matching you already have, and you can't extend it any further. Maximum means that you can start over and find a better matching than the one you've got. A matching is perfect if every vertex is represented. This requires that G has to have an even number of vertices if every vertex is matched. And so not all graphs will have a perfect matching. How about this graph? Does this graph have a perfect matching? It has an even number of vertices. There are 5 in each of these clusters. So there are 5 up here, 5 over here, 5 over here, and then 1 more in the middle. So that's 15 plus 1 is 16 vertices. So we have an even number of vertices. But here's the problem. This vertex, if we had a perfect matching, this vertex would have to match to one of these neighbors. And I don't care which one we match it to. If we match it to one of the neighbors, then what we have left are 2 disconnected pieces with an odd number of vertices. So I cannot match these 5 vertices together perfectly, and I can't match these 5 vertices together perfectly. And so I will always have some unmatched vertices. And so this graph does not have a perfect matching, even though it has an even number of vertices. As soon as I match this middle vertex up to one of the little envelopes that surrounds it, the other 2 have an odd number of vertices, but they're separated from each other. And so there will be 2 vertices left over here that won't get matched up. So we have to have an even number of vertices in order to have a perfect matching, but having an even number of vertices is not enough to guarantee it. So let's look at another definition. Say that we have a matching. An augmenting path is a path that starts with a vertex that's not matched, and then the path goes through and alternates edges. This edge is in the match, and so these 2 vertices are matched. And then this edge is not in the match, but this edge is in the match. And so these 2 vertices are matched together. And so on and so forth, alternating between edges that are not in the match, edges that are in the match, but then finally ending on a vertex that's not matched. It starts and ends with a vertex that does not appear in the matching, but every alternate edge is included in the matching. I'll show you an example on the next slide. I have a graph here, and I have a matching. I have matching AB, CF, and DE. This is a maximal matching because the last 2 vertices, GH, don't have an edge between them, and so I can't match G and H together. And so I cannot improve upon this matching using the edges that I've already included. But I can find what's called an augmenting path. It starts with one of the unmatched vertices, H, and it goes to A, so that edge is not in the matching. Then A to B is in the matching. B to C is not in the matching. C to F is in the matching. F to G is not in the matching. And then we end on a vertex that's not matched. So it starts and ends on vertices that are not used in the matching, and it alternates between edges that are included and edges that aren't included. Not in the matching, in the matching, not in the matching, in the matching, not in the matching. So this is an augmenting path. Let's put the alternating path using this sort of wavy line here. If an augmenting path exists, the matching is not maximum because what I can do is take every edge on the augmenting path and toggle it. If I include this edge in the matching and not include this edge, then include this edge and not include this edge, and then include this edge, I now have 4 pairs of matched vertices instead of just 3. I've increased the number of pairs of matched vertices, and so the original matching was not maximum. If I can find an augmenting path, I can toggle edges along the graph and find a path that's augmented, find a matching that has more vertices matched than I had before. And so the original matching was not maximum. Okay? So if a graph has an augmented path, we can definitely see the graph is not maximum because I can toggle edges along that path. Edges that weren't included, we will include. Edges that were included, we will stop including. Burgess' theorem says that this is an if and only if condition. That Gm is a maximum if and only if G does not contain an augmenting path. Okay? We're going to prove this in a moment, but before we prove it, I want to show you a couple of examples. Of things that can happen here. Let's say we have this graph here. And we're going to create this matching here. I'm going to match up these 2 vertices. I'm going to match up these 2 vertices. I'm going to match up these 2 vertices, and I'm going to match up these 2 vertices. So I have 4 edges in the matching, which means 8 vertices are matched. But there were 10 vertices to begin with. This vertex is not matched. This vertex is not matched. Okay. Well, I can improve upon this. There is a better matching that matches all 10 vertices. Let me show that to you. Come on, there you go. So if we match these 2 vertices, these 2 vertices, these 2 vertices, these 2 vertices, and these 2 vertices, then all 10 edges are matched. And so this matching is not maximal. Burgess' theorem says that we can find an augmenting path that will, if I toggle along the path, I will go from this mapping to this mapping. Okay? And so the idea here is we're going to look at all of the edges that are included in exactly one of the 2 matchings. Look at edges. Included in exactly one match. This isn't a proof yet. This is just an example, but we'll look at what happens. So this edge is included in one of the matchings. This edge is included in one of the matchings. This edge down here is included in both matchings, so I'm not going to use it. This edge is included in exactly one matching. This edge down here is included in exactly one matching. This edge down here is included in exactly one matching. This edge up here is included in exactly one matching. And this edge here is included in exactly one matching. And it turns out that this is an augmenting path. It starts at an unused vertex. It alternates between an edge that's not used, because it came from over here, then an edge that is used, then an edge that's not used, an edge that is used, an edge that's not used, an edge that is used, and an edge that's not used, and then it ends at a vertex that's not matched. That's what an augmenting path is. So the graph was not maximum, and so it does contain an augmenting path. So let's look at the proof. There are two directions here. This direction is easy. We're going to prove this direction by contrapositive. Which means we're going to suppose the negation of this, assume G has an augmenting path. Then toggling edges along that path increases the number of matches. And so M is not maximum. So we're going to look at the other direction. We're also going to prove this by contrapositive. We're going to assume that M is not maximum. Then there is another matching that is maximum. So we'll call this one M prime be a maximum matching. And let S be the set of edges in exactly one of M and M prime. Now these edges have to alternate between being in M and M prime, because I can't have two consecutive edges that are both in M, because then they share a vertex. I can't have two consecutive edges being M prime because they share a vertex. Now it's possible that I will have some connected edges that form a cycle, one in M, one in M prime, one in M, one in M prime, and an augmenting path. M prime, M, M prime, M, M prime. I might have a cycle and an augmenting path. These alternate edges and these alternate edges. In fact, I may have multiple cycles along with an augmenting path. Okay. But a cycle has to, because it has to alternate, will have the same number of edges in M and the same number of M prime. Since adjacent edges in S, since adjacent edges in S have to alternate, S is a combination of even cycles and paths. There may not be any even cycles, but S is a combination of even cycles and paths. But since M prime has more edges than M, the assumption is that M is not maximum. Since M prime is maximum and M is not, there have to be more edges in M prime than there were in M. which means that the path that we find has to have more edges in M prime than it have edges in M, and so it will alternate starting with M prime and ending with M prime. I can't find more edges in M prime in an even cycle because they alternate. Since M is M prime and is not M is not at least one path, has an odd number of edges, and its first and last edge are in M prime. This is an augmenting path. And so we have finished this proof. We assumed that M was not maximum. That's the negation of this part. And we showed that G does contain an augmenting path, which is the negation of this part. So the presence or absence of augmenting paths is a absolute ironclad test for whether we have a maximum matching or not. Okay? So we're going to look at, in a little while, we're going to look at a connection between perfect matchings and bipartite graphs. This seems kind of natural. If I'm matching up vertices to other vertices, that sounds like the way that bipartite graphs work. But the connection is not automatic. If I have a bipartite graph, can we conclude that G has a perfect matching? And the answer is no, because a perfect matching has to have an even number of vertices. And a bipartite graph does not. I could have this graph here that has 3 vertices in X and 2 vertices in Y, and have edges that connect from X to Y. But they won't have a perfect matching because there are 3 vertices to be matched over here and only 2 vertices to be matched over here. So bipartite does not automatically guarantee a perfect matching. Suppose we have a graph that does have a perfect matching. Is that graph automatically bipartite? The answer to that question is also no. I have 2 vertices over here. I have 2 vertices over here. I match X to Y. I match X to Y. This is my matching. But then I also have this extra edge here. And this extra edge here. And now I have an odd cycle. And this odd cycle means that a graph can't be bipartite. I can have edges that are not in the matching. No, because G can contain edges that are not part of the matching. Okay. So automatically, there's no connection between perfect matching and bipartite. We're going to have to do a little bit of more work to do that. So if we have a bipartite graph with partite sets X and Y, we say that one of the sets can be matched into the other set if there's a matching that uses up all of the vertices in X, even if there are vertices of Y left over. Let me show you an example. In this graph here, I can have a matching from Y into X. Every graph, every vertex in Y got matched up, even though there's a vertex in X that's left over. Now, if both sets can be matched into the other set, then we will have a perfect matching. But what we're going to call this is kind of the idea of having a matching that's perfect only on one side. Everything in Y got matched up, but something in X got left out. Okay, Y can be matched into X, but X can't be matched into Y. this is also a bipartite graph, and even though x has 3 vertices and y has 3 vertices, it's not possible to match either set into the other. Both of these vertices in x, there's only one way to match them. They both would have to match up to this vertex, and we're not allowed to repeat a vertex in a matching. And then both of these vertices in y, they both have to match up to this vertex down here, and that's not allowed either. And so it's not possible to match the things from x into y. It's not possible to match the vertices from y into x either. Neither direction is possible. Okay? So just because the two partite sets have the same number of vertices does not guarantee that we can have a match for either set of the other. But here's a theorem that gives us a test to see if we can match into another. If S is a set of vertices in a graph, S will usually contain some of the vertices, not all of them. Then N of S is going to be the set of all the vertices that are adjacent to S. So let me go back to this slide, previous slide, and do a couple of examples. So I'm going to clear this out. If this vertex is S, then all 3 vertices here are in N of S, because they're all neighbors of S. If these 2 vertices are my set S, then the neighbor set of S is just this one vertex. There's only one vertex that's a neighbor to anything in S. And the fact that I have 2 vertices over here, but only one neighbor, that's the problem. And Hall's theorem says that a bipartite graph, X could be matched into Y if and only if the neighbors are at least as big as the size of the set for all subsets in X. If I have a set of vertices and not enough neighbors to match them into, then we can't do a matching. Okay? I'm not going to take the time to prove this theorem, but I think the proof is kind of obvious from the example that we've seen. Okay? What we're going to look at in the next lesson is a little bit more work that Hall did with matchings of graphs, including some work that led to a Nobel Prize in economics. That's what we're going to be looking at next time. Thanks for watching.